Okay, we're back. So, as I had mentioned, this is an example of photosynthesis down here, where we've got the carbon dioxide, the water, and they chemically combine. One thing I want to point out is notice here we've got the same ingredients on this side of the equation as we do on this side of the equation. We've got carbons, oxygens, and hydrogens. That's it. What do we have over on this side? Carbons, hydrogens, and oxygens. So the thing is, with a chemical change, we can't make a new element, but we can combine compounds in different ways to make new compounds. Um, so that whole idea is called the conservation of mass. So here's an example of the conservation of mass. Look at all the white dots that we have up here, which would be element X, and all the red dots over here, which would be element Y. We chemically combine them. Have we created something that has more mass than the original amount? No. So if we were to take and put all these compounds on a scale together, it would equal the mass of these elements together. The thing is, during a chemical reaction, you can't create mass and you can't destroy mass. All you can do is rearrange mass. So the law of conservation of mass states that mass cannot be created or destroyed in a chemical reaction. You can't do it. You can't make new mass, you can't destroy mass. Um, so here's a really good example down here, and I think your screen might have trouble catching all this. See if we can change that a little bit. So we've got baking soda and vinegar down here. We've got 38 I'm sorry, 3.861 grams, and then you mix it together. So the baking soda was in the balloon, you put it together, and look, same mass, even after the chemical reaction, same mass, even if it fills the balloon. We did not create mass, we did not destroy mass, which brings me to a fun and interesting question. Has the mass of planet Earth changed in the last 2,000 years? I ask my students about this, and they say, "Oh, but Mr. Wagner, we have buildings now. We didn't have those 2,000 years ago." And I say, "Where did all the material from the buildings come from?" "It came from the Earth." Oh. So did we actually create mass? No, we didn't. All we did was take the mass from one area and put it in a new area. So has the mass of planet Earth changed in the last 2,000 years? Not really. The only thing that's changed about the mass of planet Earth is we've sent some satellites into space. Some students have said, Mr. Wagner, there's a lot more people on Earth than there has been in the past. I agree, that's true. But the mass of me comes from the food that I eat. And the food gets its mass from the Earth and carbon dioxide. So overall, has the mass of the Earth changed? Not really. No, it hasn't. And if we fast forward a million years into the future, which I don't know if Earth will be here, but the mass will probably relatively be the same on planet Earth. Here's another example of the law of conservation of mass. Is the law, it says, is the law of conservation of mass still true when things are burned? Well, here we've got a fireplace. And you might say, Mr. Wagner, the ashes weigh much less than the wood itself. Agree, that's true. But most of the mass of the wood is in water vapor. And whenever you take that water vapor, where did most of the mass go? Up the chimney. Does that mean it disappeared? No, you can't do that. You can't you can't make things disappear unless you're a magician. You can't do that. So in this case, the mass changed into a gaseous form and then went up the chimney. But we didn't lose mass. It's just up the chimney now. So what happens to the mass of the logs? We said the mass of the logs doesn't change. It just goes into a gas form up the chimney, and then we have the ashes. If you were to take all those gases, all the water vapor, and all the ashes and put them together, it would equal the mass of the logs. For example, 20 grams of butter, 20 grams of flour, 20 grams of eggs, and 20 grams of chocolate chips. When we put all those things together, what do we end up with? 80 grams of cookies. Is it possible to add all these ingredients together and come up with 30 grams of cookies? No. Is it possible to add all these ingredients together and come up with 100 grams of cookies? No. You That's the law of conservation of mass. All these things, all these reactants make the product, and the reactants and the products must equal each other. I'm pretty sure there's a question about the law of conservation of mass on your test. Make sure you know about that. The whole idea is relatively simple, though. You can't create mass and you can't destroy mass. Because we can't create mass and because we can't destroy mass, um, technically you have to balance equations. Now, I'm not going to make you balance equations on your test, but take a look at what we have here. We've got H2 plus O2, and over here we have two H2Os. Um, you can use, there's a web balancing equation tool online. Like I said, I'm not going to make you balance any equations, but if you did have to balance an equation, that would be a good thing to have. I think I'll put a link for that up here. And then there's a video on how to balance equations. The video is like 4 or 5 minutes. Probably about halfway through, you can stop the video. You don't have to watch the entire thing. Um, but again, it's how to make sure you're not violating the law of conservation of mass and making sure that the reactants equal the products. Okay, well, let's talk about chemical changes real quick and some what happens during the chemical change. During a chemical change, energy can be released or taken in. Mostly we think of energy being released, but it can be taken in during a chemical reaction. For example, one kind of chemical reaction is an endothermic chemical reaction. It's a type of chemical reaction in which heat is required or heat is taken in during the chemical reaction, and it causes things to drop in temperature. For example, if you add baking soda and vinegar and then you mix them, it's going to make all those bubbles, right? If you put your hand on the bottom of the container, it feels colder. That's an endothermic reaction. Endothermic reactions get colder. They take away energy, therefore they get colder. The opposite of that is an exothermic reaction. Exo means outside. So an exothermic reaction is to give off energy. It's a type of chemical reaction in which heat is giving off during the chemical reaction. So maybe you guys have seen some of those reusable hot packs. I might have one. Give me a second. I'll go check for one, see if I have one. We can demonstrate this. All right, I'm back. So I did find one. This is one of those reusable like hot hands, but to reuse it, you have to boil it. And it's got like a little metal disc on the inside. I believe it's sodium acetate. I forget exactly what it is. But what you do is you click this little metal disc in here, and you're able to get an exothermic chemical reaction. Oh, and it just started. So it turned into a slushy, and now it's really really getting warm. And I use this for give these things to Shiloh whenever we're getting into the truck on a really cold day. So this is an exothermic chemical reaction. Now they also make reusable cold packs, or I'm sorry, single-use cold packs. And you can find the single-use cold packs. You can find those at like Kroger or Walmart or something like that. And with those single-use packs, basically you mix two chemicals together and it goes through an endothermic chemical reaction and it gets really, really cold. And you can put it on an injury for like football, basketball, or track or something like that. So they make packs that go through exothermic chemical reactions like this. And they also make packs that go through endothermic chemical reactions where it gets cold. And I'll put up a link for the reusable hot packs and you can see one in a little bit more detail how it goes through an exothermic chemical reaction. Here's another exothermic chemical reaction. Sparkler gives off light, gives off heat, gives off smoke. Let's keep going. So, in order for a chemical change to occur, you actually need energy in order to make it occur. Think about matches, for example. Matches don't burn on their own, you have to get them started. So, to get them started, that is the activation energy. You need to put energy into it, and then once you get it started, it goes from there. So here's kind of a visualization to represent activation energy. You see someone pushing a stone just a little ways up a hill, but they're getting a lot more energy out overall. That would be the same idea as with matches or fireworks or gasoline. You just need to add a little bit of energy to get it started. And then once you get it started, you'll get a lot more energy out. So the energy required to begin breaking bonds to start a chemical reaction. That's the activation energy. It says, notice in the potassium chlorate, and this is the potassium chlorate, in order to begin the chemical reaction, um, it's what do you see? It's heated in order to begin the chemical reaction, and then a great amount of energy is released. Oh, I'm sorry. not this thing. This isn't the potassium chlorate. It's the gummy bear chemical reaction. I'll put a link up there for the gummy bear chemical reaction. And basically, it's sugar and potassium chlorate superheated, and it starts giving off a lot of energy. But it doesn't go on its own. You have to give it activation energy to get it started. All right, let's continue with chemical changes. The rate of chemical reaction, or the speed at which a chemical reaction takes place, depends on a few different factors. The factor that affects the rate of a chemical reaction could be the temperature. For example, if you put all the materials together to make bread or to make cookies, there's baking soda that goes in there, and it starts a chemical reaction when you add baking soda to the cookies. But you speed up the chemical reaction by heating it. So baking cookies or bread, the decomposition of roadkill or the rusting of metal, all those things speed up the chemical reaction whenever you heat them. All are accelerated with greater temperatures. And then it says keep your batteries in the refrigerator. I could take my computer upstairs and show you, but all our batteries are in the refrigerator. Batteries go through a chemical reaction, right? Well, I don't want my batteries to expire. So I keep my batteries in the refrigerator and it slows down the chemical reaction. If I were to heat up the batteries, it speeds up a chemical reaction. Have you tried starting the car in the wintertime? The battery's really, really cold. And since the battery's cold, it slows down the chemical reaction and it's harder to start your car. In the summertime, when your battery's all nice and warm, the chemical reaction increases. So it's easier to start your car. Um, Also, the concentration of a substance affects how fast the chemical reaction occurs. If you were to put just a tiny, tiny, tiny amount of baking soda inside cookies, it's not going to have a very strong chemical reaction. Your cookies or your bread's not going to rise very quickly. But if you put in cups and cups, I'm sorry, um, milliliters and milliliters or liters, and you put that inside your cookies, you'll have a very, very large chemical reaction. So it depends on the concentration. Um, Also on the surface area. What I mean by surface area is like a sugar cube versus sugar. The sugar cube has 6 sides to it, but when you crunch it up, it's got more surface area. Think of eating a Jolly Rancher. The Jolly Rancher candy, it's just got 6 sides. You put it in your mouth and it takes a long time to dissolve. But if you crunch up that Jolly Rancher or a mint or whatever, once you crunch it up, it has more surface area and it can dissolve faster. Same thing with chemicals. They can go through a chemical reaction faster when they're crunched up and they have more surface area. That's why we don't add blocks of baking soda to cookies. We add powdered baking soda to cookies to increase the surface area. And also a catalyst. Star this one. There's a question on your test, I believe. It's a substance that increases the rate of a chemical reaction without itself going through any permanent chemical reaction. The way I explain it to my kids is I say, I give an example. I say there's Sarah, Jill, and Scarlett. And I say, Sarah and Jill are sitting next to each other at a table for lunch. And Scarlett says, hey, Jill, did you hear what Sarah said to you and, and said about you? And Jill's like, no, I didn't hear that. And then she says, I forget the other girl's name I was using. Essentially, she starts the fight. Scarlett is the one that starts the fight between the two girls. But is Scarlett fighting with the girls? No, she's not. She is not fighting with the girls. She started the fight. Same thing with a catalyst. A catalyst is a chemical that starts a chemical reaction. It is not part of the chemical reaction, it just gets it started. So in this thing, the catalyst was me like clicking that little piece of metal in here, and that little piece of metal starts the chemical reaction. That would be the catalyst. So a catalyst makes a chemical reaction get started. It doesn't take part of the chemical reaction, it just gets it started. Here's a fun video. Highly recommend watching this video. It's a TED Ed video about how to increase the speed of a chemical reaction. I'll be honest, it's a little corny, and they don't go word for word with what we use, and they actually identify 5 things that you can use to increase the speed of a chemical reaction. But the overall idea is there, that you can increase the speed of a chemical reaction by concentration, surface area, a catalyst, temperature. Anyway, we're going to have to stop this video here and go on to our third installment, which will not be quite as long. So video number 3 is coming right up. Find the link for that.